So first, a few cheesy words about me. So I'm Philip. Hi, everyone. Thanks everyone for coming tonight. And so software development is what I'm passionate about. And so I'm particularly interested in functional programming and Scala. I joined ITV in January, and I'm really enjoying working here. And if you're wondering about my accent, one of my parents is German, one is English, my mother tongue is Italian. So if you ever need to find me on Twitter, you can find me on Twitter. I do a lot of slide decks on functional programming subjects, and I've been keeping them on SlideShare, but SlideShare recently has become, it's not free anymore. So I started moving them over to SpeakerDeck, and also to this dedicated site that I have, fpilluminated.com. It's very basic. All I've got there is slide decks. And at the moment, there are only a dozen. And so this one here, the top one, and Queen's Combinatorial puzzle, that will go up tonight. And so this page will go up tonight, and then you'll see the slides, you can download the PDF, you can go to the GitHub repo, etc. And so this will be the repo that I will make available later today. So let's get started. So this talk, really, I would normally like to do it in an hour, but I've been given about 40 minutes, which is kind. So I'll be rushing in places, so please bear with me. If you get confused by anything, don't worry, because you have access to the slides, the code, everything. Eventually you'll get the video. So, okay, so I aim to finish in about 40-45 minutes. So I'm going to get started. Okay, so in the 8 queens puzzle, what we're trying to do is to place 8 queens on an 8x8 chessboard, so that no 2 queens are on the same row, the same column, or the same diagonal, i.e. no queens hold each other in check. So how many ways are there of placing the queens? So for the first queen, I have a choice of 8 times 8, 64 cells. For the next queen, I have one less cell that I can choose from, 63, and so on, until I get to the 8th queen, at which point I have 57 cells left where to put it. So if we do the math, there are more than 178 trillion ways of doing that. So, but you can arrive at the same configuration in different ways. So for example, that configuration, in how many ways can I pick the queens? For the first queen, I can choose from 8. For the second one, I can choose from 7, and so on, until I get to the last queen, at which point there's just one left. So if we do the maths, there are more than 8 factorial, 40,000 ways of arriving at the same configuration. So now, if we want to know the number of ways I can arrive at a unique configuration, then I divide that number by that one, and we find that there are still 4 billion ways of doing that, right? Now, we can drastically reduce the problem space if we take into account that no 2 queens can be on the same row. So what we're going to do is, we start at the top row, we go downwards, on each row we place 1 queen. There are 8 ways of doing that on each row. So if we do the maths, we see that there are 8 to the power of 8, still more than 16 million ways of doing that. But we also know that no 2 queens can be on the same column either. So what we can do is, as we go down, we make sure that we only pick a column that hasn't been picked before. So if we do that, then this number comes up again. So there are still more than 40,000 ways of doing this. Now, we still have to take into account that no 2 queens can be on the same diagonal, but nevertheless, we've shrunk already a lot. So this gives you an idea of where we're headed in terms of the number of boards that we need to consider as candidates, potential solutions to the puzzle. So let's try to find a solution to the puzzle. We place the first queen, we cross out the cells that are now no longer available because they're held in check by that queen. We place the second queen and cross out. Place the third queen and cross out, and so on. And we get stuck. We can't place the 6th queen because all the blank cells in that board are held in check by the previous 5 queens. So we're stuck. Let's try again. So we've placed the first queen, the second one, the third one, and with a bit of luck and a bit of ingenuity, we hit upon a solution. Now, this puzzle has always featured in the official Scala book and the official functional programming, Scala functional programming book, co-authored by Martin Odersky. That's because this kind of puzzle is particularly suited to solving with 4 comprehensions. So the 8 queens puzzle is a special case of the n queens puzzle, where you place n queens on an n by n chessboard. there are solutions for all natural numbers except 2 and 3. So, in the book, the way we represent a solution is as a list of pairs. Each pair tells you the row and column where a queen is situated. And the rows and columns, they start at 1. In the course instead, the rows and columns, they start at 0. And because it's obvious that the nth queen is going to be on the nth row, we don't need to be explicit about it. The solution is just now a list of columns. That's sufficient. So in the course, Odersky gives us some code to display a candidate board on the console. And here's the code. I've tweaked it slightly to use, so I'm using a cross for an empty cell and a crown for a populated cell. And so if we pick a candidate solution, that one for example, we feed it to the show function, and then we print the result, we get this, which is pretty good. But now let's see how we can use the Doodle graphics library to draw an image of a candidate board. So we can easily create a 100 by 100 red square and a blue one. And then in Doodle we have a function called beside. You give it 2 images and it returns you an image of, which is the first one beside the second one. There's also an above function. You give it 2 images and it gives you a composite image, which is the first one above the second one. So what we can do now is, if we have a solution, we can create a square image for each of the cells of the board, a white square for the empty cell, a red square for the populated cell, and then we can use the beside and above functions to stitch together all the images into a single image for the whole board. So let's make ourselves a white square and a red square, and now we can write ourselves a combine function. So it takes a grid of images and it produces a single image for the board. So the way it works is, first it maps over the rows of square images. So for each row of images, it reduces it using the beside function. So stitches together the images side by side and creates a single image for the row. So it does that for every row, and then it reduces the row images with the above function. So then they get stitched one on top of the other. So now we have an image for the board. So that's the code we have, but it's a bit unsafe because, as you guys know, if you call reduce on an empty collection, you get an exception. So to be safer, we use fold instead. Now, to do that, we need to tell fold what to return when the collection is empty. So we tell it to return an empty image. And also, fold is just an alias for fold left. So let's be explicit about that. So our combine function is using fold left. Now, for this section of the talk, we need the concept of a monoid. So for the purposes of this talk, a monoid is just 3 things. It's the values of a type, for example, integer numbers. And the second thing is a binary associative operation. In our example, because we've got integer numbers, we're going to have integer addition. That's the binary operation. And then third, an identity. So for us, the identity is going to be 0. The identity for addition is 0. So in the red book, in the foldable trait, we see a concatenate function. It operates on a foldable of A's. So for example, a list of A's, right? And notice it takes a monoid for A. So what concatenate does, it does a fold left for us, where the initial accumulator is the identity of the monoid, and the binary operation is the binary operation of the monoid. So this operation in cats is called fold. There's also a combinatorial alias to avoid clashes with the fold that is in the standard library. I'm going to skip this intro to monoids. I'll be doing a bit of this, sorry, it might be a lot. Okay, so this is the code we have at the moment. So now what we can do, using cats, we can define a monoid. Now, the identity of the monoid is going to be the empty image. The binary operation is going to be the beside function. And for lack of imagination, I'm going to call the monoid beside. So then what we can do, instead of doing a fold left with an empty image and a beside function, we can do a combinatorial with a beside monoid. Now, in the foldable trait, there is also a fold map function. That builds on top of the functionality provided by concatenate. Notice it takes an extra parameter f, a function from A to B. So logically, all it's doing is it maps all the A's to B's, and then it proceeds like concatenate does. It folds the B's, right? That's why the monoid is for B this time. So fold map, so it does a fold, so it does a map, and then it does a fold. And fold map is called the same in CADS. So this is the code we have at the moment. So what we can do is, to make things easier to understand, I'm going to temporarily revert to the unsafe approach, where I'm using reduced, because I want to spell out for you that what we have here is a map of a function followed by a reduce with another function. And so now mapping and reducing, mapping and folding, is what fold map does, the function that we've just seen. So we're going to use that instead. Let's define another monoid. The identity is still the anti-image. The binary operation is now the above function. Let's call it above. And so what we can do is, instead of mapping a function and then reducing with the above function, we now fold map the function with the above monoid. So it's getting simpler. And this is the small journey we've been on so far, from end start point to end point. And yes, it produces the same result. We've refactored, right? And now if we go back to our show function, where it currently uses a cross and a crown, and where it stitches together smaller strings into larger strings, we're going to make square images, an empty one and a full one, and we're going to put them in a grid, and we're going to pass the grid to combine, and combine is going to spit out an image for the board. So, but we can do a bit more though. In the images we've been making up to now have been centered on the origin of the coordinate system. But in Doodle, there is an at function on an image. You can say at, and you can give it a coordinate pair, and that places it at an absolute place, right, on the coordinate system. That's a compromise. I mean, if you're prepared to do that, then we can go further. What we can do is, instead of using the beside and above monoids, we can declare a third monoid. The identity is still the anti-image. The function is now on. What does on do? You give it two images, and it places one on top of the other. It superimposes them. Don't worry about that, because we are placing them at the right location. So when you superimpose, you're really getting a richer image, but they're not obstructing each other. So let's call the monoid on. And now we can, instead of using beside and above, we can use on anywhere. I'm speeding up because I need to go fast. So we're using the on monoid. In the final step, let's make the monoid implicit. So we're saying in our program for images, the default monoid is the on monoid. And if we do that, fold map and Combinatorial in CADS are happy to take the monoid implicitly. So this is the refactoring journey we've been on. And hopefully you'll agree that the bottom function is simpler if you understand fold map and Combinatorial and the fact that there's an on monoid somewhere. So earlier we looked at the number of ways of placing 8 queens on a board, one on each row, and we came up with these numbers, 8 to the power of 8. That's the number of permutations of 8 queens allowing repetition, i.e. that allows multiple queens to be in the same column. At the bottom, 8 factorial, that's the number of permutations without allowing repetition. So for arbitrary n, the formula is n to the power of n and n factorial. So how do we compute the permutations of n queens, for example, for n is equal to 4? We can use this simple code. It picks a column between 1 and 4 for the first queen, then it does the same for the second, the third, and the fourth queens. It puts the results in a list, and it yields the list. The full comprehension yields the list. And if you run that code, you get the list of all the permutations of columns 1, 2, 3, 4, allowing repetition. Notice in some of the permutations you see numbers repeating, right? And if we were to print some stats, we'll find that yes, the number of permutations we've just seen is 4 to the power of 4, 256 permutations. And here they are. I've made the squares, the square images, I gave them to our combine function, and this is how it displays them. There are 256 permutations. The question is, how many of these are solutions to the puzzle? And the answer depends on n. For n4, there are only 2 solutions to the puzzle. And here they are in green. Those are the solutions. The question is, how do we find the solutions? And Odersky suggests using recursion. So let's do that. Let's refactor our function it's not actually, yeah, so let's revisit it to use recursion instead. So the way we compute the permutations for n queens is, first we compute the permutations for n minus 1 queens. Now, that's going to start us a chain of recursive calls. The base case is going to be when n is 0, n queens. Sorry, 0 queens. When there are 0 queens, the number of permutations is just 1, the empty permutation. So that's the result. We start coming out of recursion. So we've got ourselves a partial permutation. Now, so that's in queens. Now we pick a column between 1 and 4 for the next queen, and then we cons the queen onto the queens to make a fuller permutation. And that works. We get exactly the same result, which is what you want when you refactor, right? So recursion is neat. And this is the code for the n queens puzzle in the book and in the course. And you can see it's pretty much the same, although you'll see at the bottom there is an is-say function that we haven't discussed. So on the left, you see the permutations code that we just saw earlier. So you can see it's hard-coded to work for n is equal to 4. On the right, you see the n queens puzzle that we saw on the previous slide. And you can see it's using the same approach with the for comprehension, with recursion. But you can see that it's generic. It works for an arbitrary n. And also, it uses this is-say function that we haven't talked about. So the only thing we're going to say in this talk about the is-say function is what it does. So it's going to be a black box for us. What it does is you give it a permutation built so far, the queen's placed so far, and you give it a proposed location for the next queen, and it tells you yes or no, true or false, is it safe to place the queen there? And the way it does that is it checks that no two queens are on the same row, the same column, or the same diagonal. So let's revisit our permutations function and use the is-say function in it. So once we've got our permutation, partial permutation, and so on, once we've picked a column for the new queen, we then ask, is it safe to place the queen there? And only if it is safe do we proceed. Otherwise, in the for comprehension, we backtrack. And if we do that, the vast majority of the permutations are discarded as unsafe, and we're left with just two, which are the solutions that we saw earlier. So this is working, using the is-say function. It's helping us to find the solution. Let's visualize how the filtering reduces the problem space. We start with an empty board. We place the first queen. There are 4 ways of doing that. For each of those ways, we place the second queen. Again, there are 4 ways of doing that. The is-say function kicks in. I've marked in yellow the boards which are unsafe. We're going to ignore those. For the white boards that are remaining, we place the third queen. Again, there are 4 ways of doing that. Again, there are some unsafe boards in yellow. I've also marked in orange with some placeholders the boards that are not generated, that alone check for safety because they originate from unsafe boards. So this is where our algorithm is being slightly smart. It says, I'm not going there, it's pointless. So now, for the remaining white boards, the safe ones, we then place the fourth queen. Again, there are 4 ways of doing that. And again, you see unsafe boards, boards we're not even generating, and you see the 2 boards that are the solution. So our code has generated 60 boards out of potential 256 that you could dream up, and it found 2 solutions. That's for n is equal to 4. When n is 5, there are 10 solutions. When n is 6, there are 4 solutions. When n is 7, there are 40 solutions. When n is 8, there are 92 solutions. You can see that the number of solutions varies widely depending on the n. So here's the code for the n queens puzzle in Scala and in Haskell. This is recursive. I went to the Rosetta code site and I looked for alternative solutions to the puzzle in Haskell, and I came across this one that it does not use recursion. It uses a function called for_them, which I had never seen before. And the variable names it used, I didn't find very useful. And it was succinct, but it relied on lots of comments. So I thought this means it's difficult to understand. So what we're going to do for the rest of this talk is understand how for_them works and see how it can be used to come up with an iterative solution to the n queens puzzle. So we're all very familiar with the bread, butter, and jam of functional programming. That's map, filter, and fold. So to understand for them, we're going to look at the monadic variant of this triad, which is mapm, filter n, and fold n. So let's start with mapm. I came across mapm in this Haskell book. We're all very familiar with the map function. It takes a function from A to B, a list of A's, and it turns them in a list of B's, right? But what we want to understand is how the mapm function works. And we can write the code for mapm ourselves in Scala using the cat's monad type class. We're going to look at this code soon. But in the meantime, where does mapm live in Haskell and in Scala? So, as Runa Bjarnason says in the Red Book, in Scala, if the question is how do I do this, the answer is either don't do it, or traverse, or its companion function sequence. Now, we're going to skip the intro to sequence and traverse, because we don't have time. And now, in Haskell, traverse lives in a traversable type class, and it's based on applicative. Now, let's compare the signatures of map and mapm. So, we're all familiar with map. Notice the function we pass to map returns a b. The function we pass to mapm returns also a b, but in a monadic context. Now, the overall result of map is a list of b's. The overall result of mapm is also a list of b's, but in a monadic context. So it turns out that in Haskell, mapm is just traverse. And in cats, we can find the analogous function traverse. So we can write ourselves some boilerplate that you can ignore, which defines mapm in terms of traverse. And now, I'm kind of not surprised that mapm is just traverse, because that's what traverse is. It's so generic that it's so powerful. In the Red Book, I had my mind blown a couple of times when I learned that you can define map in terms of traverse, which is so essential, so basic. And you can define full map, the function we saw earlier. They can both be defined using traverse. So I'm going to skip these functions, these slides which are interesting, but we don't have time. So let's look at an example of using mapm, where the monadic context is an option. So at the bottom of the slide, you see some Scala code. There's a convert function. It takes a char and it returns an option of an int. It tries to convert the char into an integer. So in the first assertion, one of the chars is not a digit. So at some point, convert is going to return none. When that happens, mapm is going to short circuit and also return none. In the second assertion, all the chars are digits, so convert always returns a sum of an integer. Now remember, mapm is traverse, so it's going to turn a list inside out. It's building a list of option of in. It's going to turn it inside out into an option of a list of in. And that's why you get the result sum list 1, 2, 3, 4. So that's the first example with mapm. That's with option. Now let's look at an example with list. So mapm may return 0, 1, or more answers. So we all know map. So if we call map on the list x and y with that simple function, we know what's going to happen. X is going to get combined with 1 first, then with 2. Then it's y's turn. It gets combined with 1, and then with 2. And so that's the obvious answer, right? But what happens when we use mapm instead of map? So we're calling mapm on the list x and y. At the head of the list, there's an x. So we pass the x to f. We get list x1, x2. We are in a for comprehension, so we pick the first element x1. We then go into a recursive call to mapm. That's on the tail of the list. At the head of the tail, there's a y. We pass the y to f, we get list y1, y2. We pick the first element, y1, we do a recursive call. This is now the base case. The result is a list with the empty list. We come out of recursion, we pick the first element of the list. Remember, we're in a for comprehension. And then we cons the y1 onto the empty list. Then we switch to y2 in the for comprehension. We do the same recursive call, which is the base case. We come out of it, we pick the empty list. We cons y2 onto it. We come out of recursion. Now we've got list with list y1 and list y2. We're in a for comprehension, so we pick the first element, list y1. We cons x1 onto it, and we have the first element of our answer. And now that you've seen how the sausage is made, I'm just going to fast forward to the rest, because it's painful. And so that's the answer. And you can see it's quite different from the result, the answer that map gives. And you can see the list monad hard at work to combine things in as many interesting ways as possible. I have an example with the I/O monad, but we don't have time to go through it. It's interesting. Please look at it in your own time. Remember, you have the slides and everything. That's MapM introduced. Let's move on to filter M. I came across it in the same Haskell book. Again, we can write the code for it ourselves in Scala using the monad type class in cats. This time, we're going to compare the code of MapM and filter M. So where MapM takes a function that takes a name, returns a b in a monadic context, filter M, the function is called p for predicate. It also takes a name, but it returns a boolean in a monadic context. And where MapM extracts from the call to f a b and extracts from the recursive call a list of b's, and where it conses the b onto the b's, what filter M does is it extracts from the call to p a flag, the flag that tells it whether or not to keep the current element. And then it extracts from the recursive call to filter M the a is retained so far. And then, so what filter M does then, it says, well, if I'm retaining the current element, I'm going to return the result of consing the current element onto the a's retained so far. Otherwise, I'm just going to return the a's retained so far. And where does filter M live in Scala? We can find a filter array that uses applicative intraverse filtering cats. Again, we can write ourselves some boilerplate that you can ignore. It allows us to define filter M in terms of filter array just for convenience. And let's look at an example, again with the option as the monadic context. So we've already seen this example with MapM. Let's adapt it to serve as an example for filter M. So bottom right in Scala, you can see a maybes even function. It takes a char and it returns an option of a boolean. So it tries to convert the char into an integer. If it succeeds, it asks, is it even or not? So it returns a flag in an option. Now in the first assertion, one of the chars is not a digit, so maybes even is going to return none, so filter M is going to short circuit and return none as well. In the second assertion, all the chars are digits, maybes even always returns an option. So it returns sum of false, sum of true, sum of false, sum of true in this particular case. Then filter M peers into the options, consults the flags and works out what to keep. And not surprisingly, it ends up keeping the two chars that map to even integers. So that's option. Let's look at an example. The monadic context is a list. It turns out that if you pass to filter M a function that ignores its parameter and always returns a list with both true and false in it, so in other words, I want my cake and eat it. I want to both keep the current element and discard it. If you do that, what it returns is the list of all the sublists of the input list. So that's the power set function. The set of all the subsets of a set. That's an example of the value. And let's see it in action. Let's do a filter M on an empty list when that's the base case. So the power set of the empty list just contains the empty list. If now we filter a list with a singleton list with one element, say 3, then what filter M does, it takes the lists in the power set and then it both conses and refrains from consing the current element. So cons and not cons, so you get a new power set with 2 lists in it. And then again, if there's one more element, again cons the current element onto all the elements of the power set, refrain from consing the current element from all the elements in the power set, and so on and so forth. And you can see that it does indeed compute the power set. Now, that's filter M introduced. Now let's move on to fold M. This is the one that we're going to use to solve the puzzle. So we're all very familiar with the left fold. The left fold takes an initial accumulator, a binary function. It applies the function to the accumulator and all the elements in the collection, going from left to right. So a simple example, here we're folding some integers, starting with a 0 initial accumulator, and the binary operation is addition. So not surprisingly, it just adds them up, and the result is 14. Now let's compare the signatures of the left fold with fold M, the one we are interested in. where the left fold takes a binary operation that returns an A, for them takes a binary operation that also returns an A, but in a monadic context. And where the left fold overall returns an A, for them also returns an A, but in a monadic context. So you can find for them in foldable, in cats. So let's look at an example where the monadic context is an option. So if you look at the bottom of the slide, there's some Scala code. The bin-smalls function, it takes an integer accumulator, an integer current element, and if the current element is too large, it returns none. But if it's not, then it adds it to the accumulator and returns that in a sum. So in the first assertion, one of the integers is too large. So bin-smalls returns a none, and therefore for them short circuits and returns a none. In the second assertion, all the integers are small, so bin-smalls always returns a sum of an in, and so for them is really now behaving like the playing fold. It adds all the numbers up, except that you get result 14, the same as before, in a monadic context, in sum 14. Now that's easy to understand, but when the monadic context is a list, it gets trickier. The thing is, that's precisely what we need to do to solve the n-queens puzzle. So we're going to look at 3 examples of using for them where the monadic context is a list. And before we do that, let's look at the definition of for them again. So if we look at the pseudocode in the bright white box there, so for them takes a binary operation f, an initial accumulator, and a list of elements. And what it does is it continuously calls the binary operation with the current accumulator and the next element. And then it extracts from the monadic context the next accumulator. And it keeps doing that until it gets to the last element, at which point it just does one more call to f with the last accumulator and the final element. And it just returns that, because as you know, for them returns a value in a monadic context. We're going to skip these slides. And now, so let's look at an example where the monadic context is a list. Now, to understand what's coming up, focus on this, where a plain fold manages one accumulator. For them manages 0, 1 or more accumulators. That's where the complexity comes in. So let's look at the first example. We're going to pass to for them a very unlikely function. It ignores its parameters, the accumulator and the current element, and always returns 2 zeros in a list. Now, if we fold an empty list, for them says, I'm just going to return you the initial accumulator, it happens to be 9 in a list. If we fold a singleton list with, say, 1 in it, for them now has an accumulator, the 9, right? So because it has one accumulator, it calls the function once, that produces 2 accumulators, and so that's where we are at the moment. And so this is how it unfolds visually. You can see that at any time, the accumulators are doubling. So at any time, the number of accumulators is 2 to the power of the size of the input list. In the next example, we're going to make things a bit more realistic, and we're gonna make it look a bit more useful. So instead of just dumbly returning 2 zeros in a list, we're still going to return a list with 2 elements, but we're going to build them by both adding and subtracting the current element from the accumulator. So this is how it unfolds visually. You can see again that the accumulators are doubling every time. It looks a bit more useful. We're adding, subtracting, we're computing something, right? And if you squint, if you were to look at it, in the values that you see in these lists, you will find the 2 values that would be returned by a plain fold if it did addition or subtraction. So that's the second example. Now in the third example, what we're going to do is change the type of the accumulator from an integer to a list. And so the function we pass for that, now what it's going to do is going to both cons the current element onto the list accumulator and refrain from consing it, both things again. So this is how it unfolds visually. And you can see here the accumulators, they're not doubling every time. And so what's happening is that, forgive me, they are doubling every, I'm thinking of the next slide. So, so again, third example, same approach. So the accumulators are doubling every time. And some of you will have noticed that it's the power set again. So we found another way of computing the power set using for them instead of filter n. Not as nice. I'm going to skip this. And so that's filter M introduced. Now let's move on to fold M. So now that, yes, let's see how can we use fold M to solve the n-queens puzzle. We're going to use it to generate the permutations of a list of integers. These integers are really the columns for where we put the queens. So we already have code to compute the permutations, but this code allows repetition. We don't want that. We want to compute permutations without allowing repetition. So if we have n elements, we want to compute n factorial permutations. If we have 3, for example, we want to compute 3 factorial, 3 times 2 times 1, 6 permutation. You can see the permutations, the numbers never repeat, right? That's what we want to solve the puzzle. We can do that by passing to fold M this function, update. So update takes 2 parameters. It ignores the second one. The first parameter is the accumulator. It contains a permutation built so far, and then the choices that are still available. So what update does, for each of the choices available, it constructs a new accumulator whose permutation is built by taking the current permutation and consing onto it the selected choice. And then the choices are constructed by removing from the current choices the selected choice. So what happens is that permutation keeps growing from partial into fuller, and the choices keep shrinking. As we choose columns, we have less left to choose from. And it works. If we pass fold M the update function with an accumulator that has the empty permutation and the list of items to permute, and then we apply that to the same list, the thing is, the contents of the list, the second list, don't matter. It's the size that matters, because they govern how many iterations it's going to perform. But obviously it's convenient for us, we use the same list, right? So that works. You can see the permutations there, except that they are nested inside a pair and they've got some noise, some empty lists next to them, right? So we're going to need to deal with that soon. So let's see how that unfolds visually. And so this is where I got confused earlier. So here's where you notice that the accumulators are no longer just doubling like before in the previous examples. Here what's happening is that for the first iteration, for the one top accumulator, we have fold M has to find an integer. There are 3 choices. So that results in 3 accumulators. Then in the second iteration, for each of those accumulators, again it has to pick an integer. This time there are only 2 choices. So 3 times 2, that leads to 6 accumulators. In the third and final iteration, it has now 6 accumulators. In each of them it has to choose an integer. Now there's only 1 integer left. So that leads to, again, 6 accumulators. So you can see here the accumulators, instead of doubling, what they do is they grow like the computation of n factorial. 3 times 2 times 1 is 6. 6 accumulators. And you see the permutations in that we're looking for, right? So we're going to need, I'm going to skip over this boilerplate code to get rid of that noise, the empty list, the fact that what we want is in a pair. So what we're doing now is, our domain is the n-queens puzzle. So let's do some renaming. The update function, let's rename it to one more queen. And the permutation built so far, let's rename it queens. The queens we have already placed. And choices, let's rename that empty columns, the columns where we still have an option to try and place a queen. And next, we don't want all permutations, we want the save permutations. So let's plug in this black box, the isSave function. So once we got ourselves, we picked a column for the next queen, we then ask, is it safe to place the queen there? And only if it is safe do we proceed, otherwise we backtrack in the full comprehension. So in the previous example, that's how we called fold M. But now what we're doing is we're writing a queens function that takes an integer, say 4, and it returns you the solution, say 2 in this case. So this is how we need to call fold M now. The function we're passing to fold M is not updated. We've renamed it to one more queen. And we're not folding 1 to 3, we're folding 1 to an arbitrary n. And finally, we know that in the result, we get the permutations, but they're nested in the pairs and there's some empty lists. So at the end, we map over the pairs, we extract the head, so we've got our permutations. And here you have it. This is the iterative solution to the n-queens puzzle using fold M. And for completeness, I've plugged in the is-safe function, which we're not going to talk about any further. So we've gone from a recursive algorithm to an iterative algorithm. And here's the code with some unimportant modifications that I've made to the is-safe function and the helper functions. So that's Scala and Haskell. This is the transition that we've gone through, although we haven't really looked at the Haskell in detail, from recursive to iterative. And here's the original code in Haskell that was the motivation for this talk. When I looked at this code, I thought, right, okay, it's using for them. I don't know what for them is. It's got lots of comments. That suggests it's not easy to understand. The one more queen function, the variable names are not very suggestive. They don't help me. So at the bottom you can see our version. The one more queen, the names of variables in one more queen are easier to understand. At the moment I've removed the comments just because I'm not going to repeat them. And also we are now thoroughly familiar with for them. So we understand how it works. This is the transition we've gone through in Scala from recursive to iterative. And it works. And it works in Haskell and it works in Scala. And so to conclude this talk, I want to leave you with one thought. So the recursive algorithm has no memory of where it's placed queens so far. So it will happily generate a board which has queens in the same column, and then it will check them for safety, pointlessly. Whereas the iterative algorithm has memory. Remember, permutation grows, the choices shrink, and so it remembers, and so it's going to do less work, less pointless work. So yeah, I'm going to skip all of these slides, just because I'm running out of time, and I'm going to zero in on this slide. If you look at the right-hand side of this table, so when n is 4, the recursive algorithm generates 60 boards, of which 16 are the ones that have the requisite number of queens on them. I call them candidate boards. They may well be the answer that you're looking for. So 60 and 16. The iterative one does less work. It generates 32, of which 4 are the candidate boards. Now, this distinction, this difference, it persists and it widens as n grows. And so when you get to n is 8, for example, the recursive one generates 15,000 boards, the iterative one generates 5,000 boards. It's not an order of magnitude, it's not very sexy, it's not an order of magnitude improvement, but still it's an improvement. And so I'm going to leave you with this chart where you can see how the number of boards generated by the two algorithms grows as n grows. And you can see that the iterative one does less work, it generates less boards. And this is the same diagram, but here they are candidate boards, the one that are actually, that could be the solution. The other ones are intermediate ones. And that's all I have. But before I finish, I want to say, if you liked any of this tonight, really this is a new talk just for you. But the material does come from these, some of the material comes from this series of decks. So if you're interested, you can go to the places I told you about earlier and you can look at these decks maybe if you're interested. So that's really all I have. If anyone has any questions, please feel free to. Don't feel embarrassed if you don't have questions, but if you do, that's great. I can't promise to answer, but I'll try. You want them, right?
I've got a rather cheeky question, if I may. Your talk was packed full of content, very thought-provoking, so thanks. But I would like to zero in on one particular claim you made, and that is that fold is an alias for fold left.
Yes, as in Scala. If you want to look at the definition, you'll find that it takes you there. Yeah. Fold is defined as fold left.
Oh, is it the same?
By the way, I'm on Twitter, so please come and, bug me. Check it out tonight. Go check it out.
Okay. Yeah, it's just...
Haskell is slightly different if that's where you're...
Yeah, but with fold, accepts a function that takes two parameters of the same type, both of type A, and then it accumulates a result of type A.
In Scala, literally, if you go and look at the definition, that's how it is. And yeah, it is risky because if you don't have, well, the thing is, you also have to think: are you using Scala, using cats, using Haskell? Because fold is going to use the default monoid, right? That's why it's safe. But in Scala, there is no default monoid in the plain vanilla Scala. So if the collection is empty, you're gonna bomb out. If you fold an empty collection, you're gonna get an exception. So, but anyway, so fold at the moment is defined.
Doesn't fold accept like a starting accumulator? So if
No, that's the fold left. Yeah.
okay, that's a bit. Perhaps I'm misremembering the Scala
It's fine.
standard
I
library.
may also be misremembered. So come in and find me on Twitter. Yeah.
Thank you.
By the way, the code for this talk is in the repo, so you can look at all the code so that you can run it and see the results.
That was a wonderful talk. Where I lost you completely was when you introduced MapReduce.
Right.
So if you can, obviously, the examples you wanted to give, you skipped because of time.
Yeah.
If you can just skip around this synopsis of where MapReduce, and that's good, that would be appreciated.
Well, I mean, MapReduce is a workhorse in our industry, right? And that's why it's a bit of a buzzword. So, we use it everywhere. But it's just interesting that, it's a pretty fundamental notion as a function, fold map, in, say, cats, in a framework like cats. And, yeah, I mean, ultimately, it's just doing a bit more than concatenate. And so, in a way, like, concatenate is the interesting one because, it takes a monoid and so it uses the monoid to do the fold. So it's succinct, right? You don't need to bother giving an initial accumulator and one operation. You can just give it a monoid. And most of the time in Scala and cats, it's implicit. So, yeah.
Well, thank you very much.
Hey, I really enjoyed the talk. I'm a fan of both function programming and chess. What I know about the end-queens problem, not really about the problem, like a chessboard is symmetrical in both dimensions. Is there a way you could modify the solutions to kind of only have to compute half or quarter of the...
Yeah, there is. And by the way, don't assume that I dream and eat and breathe and breathe. So this is more or less what I know. It goes much deeper. Yeah, I mean there are symmetries that you can exploit. Of course, yeah. You can do much less computation. Yeah, remember this appears in a beginner's Scala book, right? It's to illustrate four comprehensions. It's very neat, right, to be able to solve with four comprehensions. But yeah, this is basic stuff. There's nothing. I mean, the end-queens puzzle side of it is really basic. I mean, I'm sure there are people in here who know more about me than me than about the end-queens puzzle.
Succinct question. I didn't really understand at the end why was it that the recursive solution had fewer. Because I thought the logic is the same.
No, you're right. No, remember, it's when you plug in the same function that you get.
Yeah, but it's the same, it's a function, so why is the iterative solution?
So you want to know why it generates fewer balls?
Yeah, exactly.
Yeah, because it doesn't have, it doesn't have memory. So the recursive solution will always check 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. It doesn't care that it's just picked 3 in the previous iteration. So now it's going to pick 3 again and then say, oh no, they're on the same column. So it's going to generate these boards and check them for safety because it doesn't have memory. The iterative one, the choices, so once it picked the column, it says, right, that's it, you can't choose that again. And so the choices shrink, and so it's smarter. So that's and actually, it's a good. I mean, ultimately, it's not that exciting. I mean, it's an improvement. I mean, I mainly showed it to you also because it's cool to see how you go from recursive to iterative, use a new function. What is for them? It's part of a family of functions, that monadic variants of map filtering fold. But ultimately, the improvement. I mean,
understand. Yeah, the recursive one could have a parameter of.
But also the recursive one is easy to understand, arguably, right?
Yeah.
I mean, the one that didn't use recursion, it looked a bit strange, didn't it? 1 to 4, 1 to 4, 1 to 4, 1 to 4. And so also, that was hard coding, also the number of columns. You can't do that if you're not hard coding, right? So you So you have to use recursion output.
Thank you. Any more at all?
By the way, I appreciate, I mean, I did kind of speed through a lot of that, so hopefully it was still pass along into the rest.
So in this example, it's perfect for the where you can have one per column, one per row. What about if you had a different limitation where you could have duplication of the information? Could you use the same approach?
When you have duplicate, so you mean
So
where?
let's say you could have 2 per column, but no more, 2 per row. Could you use the same approach?
Right. Yes, because you see, the intelligence is is save function. So the save function will check that no two queens are on the same row, the same column, the same diagonal. You can do what you like in there, right? So yeah, you could say, oh, okay, I'll remember that. Oh, I've seen 2 queens on the same column before, but I'll allow that. Oh, and then the second time you say, no, sorry, it's only once or twice. Yeah. So, but then that raises, that makes is safe more interesting, right? Because then it's got state inside it. So you use a different. You probably need some structure, right, to do that. Yeah. I mean, you can do it in a dirty way by just storing, keeping track in a variable. But we don't like doing that, right? In Scala. So yeah, but no, it's a good point. There are all sorts of things that you can dream up really to make this more interesting, more comprehensive.
Thank you.